I'd like to look at a problem, and I want to look at problem number 20. And here we are. So, A, find the approximation using tensor intervals on this integral. We're not going to do A, we already did A, kind of like the previous problem. Now, we are interested in B and C. Estimate the error in the approximation. Estimate the error in using the trapezoid, and estimate the error in using the midpoint. Well, to do that, I need to figure out a bound on the second derivative of this. Well, if f equal e to the 1 over x, f prime will be e to the 1 over x times negative 1 over x squared. So that is negative e to the 1 over x divided by x squared. If I take a second derivative, that would be negative derivative of the top times the denominator minus the top times derivative of the denominator, all over the denominator squared. So this second derivative would be negative, since that's a negative, it will become a positive. If I take e to the 1 over x out, there's a 1 plus 2x over x to the 4th. So if I could take a derivative of that and figure out where you have a maximum or a minimum, or I could look at this and say, wait a minute, on the interval from 1 to 2, since x is not a fraction or negative, right? So it's not a fraction between 0 and 1. Since it's bigger than 1, this is decreasing. And this ratio, if x is bigger than 1, that's decreasing. If I have a second derivative that's decreasing, wouldn't that mean that the highest I can get, or the maximum I can ever get, is at x equal 1, maximum of f double prime? So if I throw 1 in, wouldn't that be e to the 1 over 1 times 3 over 1? So k would be simply 3e. And once I find k, pretty much I'm set. That is, if I want to find the error in using the trapezoid, I'll say that's less than or equal to k times b minus a. B is a 2, a is a 1, right? Raised to the 3rd power, all over 12 times n squared, n is 10. And if I want to figure out the error in approximating the midpoint, it's less than or equal to k times b minus a raised to the 3rd power divided by 24 times n squared. Plug this in my calculator, and there's the error, and let me evaluate those. And these are the values I have, which means my calculation in part A is accurate to 2 decimal places. Here I have to be a bit more cautious. In this section, we just find the error. In chapter 11, we'll talk a bit more about that in more details. And if I wanted to tackle part C, which says you are using an approximation, how large should n be so that the error in those is accurate to 10 to the negative 10 to the negative 4. So in this case, I really want the error, and let's say in using trapezoid, to be less than or equal to 0.0001. Well, the error here is actually k into b minus a cubed divided by 12n squared less than or equal to 0.001. Well, I know what k is. Again, that's the key to the whole problem. 3e times b minus a, it's 2 minus 1, cubed divided by 12. N is what I'm looking for. There's an extra 0 there, right? Yep. Well, guess what? I can treat a nonlinear inequality like an equality. That's a 1. So this is simply e divided by 4n squared being less than or equal. Now, this is not a linear inequality, but since n is always positive, I am allowed to treat this like a linear inequality. And be careful how you do this. If you cross multiply, you could mess up the inequality. Just get a common denominator and solve for n. Divide both sides by and square root both sides. Again, you're allowed to do that just because n is always positive, and n should be greater than or equal. If I plug this in my calculator, I'll get 82.43. Since we want more accuracy, we round up all the time. We say, if you want your accuracy to be to 4 decimal places, not 2 decimal places, then guess what? You need to use this and let n equal 83, and then your numbers will be accurate to that many decimal places. There aren't enough problems. There are only a couple of more problems. You know, if you look at the homework only consists of 3 problems. So I want to do example 6 just to demonstrate how this works. Keep in mind, if I ask you to find how large n should be, automatically I'm forcing you to find k. So how large should we take n in order to guarantee that the Simpson's rule is accurate to the same decimal places? We're looking at the integral of 1 over x from 1 to 2, so f is actually 1 over x. If I'm using the Simpson's rule, whether I'm finding the error or I'm finding how large n should be, I need to find k, so I need derivatives. That's x to the negative 1. That would be 24 over x to the 5th. If I want to find the maximum this could ever be, again, no need to take another derivative because this function is decreasing if x is bigger than 1. Between 1 and 2, the largest it could ever be is at x equal 1. So that's the maximum of the 4th derivative, which is k. And that turns out to be 24 over 1 to the 5th, which is 24. And if I want the error in using Simpson to be less than 0.0001, well, guess what? This is k into b minus a raised to the 5th power over 180 n to the 4th, and the same idea applies. This is a 1, so this is 24 less than or equal. If I get a common denominator, I could simplify this, but I'm going to use a calculator anyway, so what's the point? This is 0.0001 times 180 n to the 4th, so n to the 4th is bigger than or equal to 24 over. Of course, I could multiply some of those. And if I plug this in my calculator, I'm getting n to be bigger than or equal the 4th root of this. And in my calculator, I got this to be 6.04. We always round up. Can you guess what n is going to equal? And why is it 8? Because if you use the Simpson's rule, n must be even. Always. Now, just checking if I gave you a page number on this, because sometimes I get excited, and I did get excited on this. So these are on page 564. And I'm going to list the homework down. And this is the homework, 7.7 on page 564, number 1, 5. Let's go 7 through 19, every other odd, 20, 21, and 27. The last three have an arrow with them, and the 7 through 19, every other odd, will be using the trapezoid and the midpoint. And that concludes this section.